Oh boy, what have I gotten myself into this time? So I didn't plan to do TCP. I thought I would only talk about some theoretical basics of it, but I've found a little bit time for it. So and because TCP actually is the most important of the network protocols, today we are going to talk about TCP and actually implement it. At least a little something that's kind of compatible to TCP. We won't implement a complete TCP implementation. So as always, the Wikipedia page about TCP is the transmission control protocol is really good. Very interesting, as usual, is the structure of the header here. So, but let us talk about some theoretic stuff first. So with UDP, you had the problem that your data might arrive in the wrong order, or it might arrive not at all. So that's useful. It's okay if you do something like video conferencing, and a lost packet will just cause a little glitch on the screen, or if two packets are the other way around, the screen might have two areas switched or something. Although I think video conferencing tools probably send some information which gives the packets an order, and if a packet arrives too late, then it's probably dropped. But TCP is different. I mean, the problem with UDP is that it operates on IPv4, and the IP network is unreliable, so it gives you no guarantee that things you send actually arrive, and it gives you no guarantee that things arrive in the correct order. Now, TCP also uses IPv4, so actually that doesn't make sense. If both of them use the same protocol, how can one be reliable and the other one not? Well, the thing is that TCP, additionally, TCP also has this stuff with the sockets and the ports, but TCP has the following behavior. So here's the RAM of the sender, and here's the RAM of the recipient of a message, okay? Now the sender sends the message with IDs, say 1, 2, 3, 4, 5. And the sender is required to store this data for some time. So let's say we send all this data to the recipient, okay? And say the first packet arrives. Now the recipient sends the information, hey, thank you, the first packet has arrived, and then the sender is allowed to delete this from his memory. Okay? And now let's say 2 and 3 arrive or let's say 3 doesn't arrive at all, 4 arrives next, and 2 arrives after 4. Then what happens is it would say, okay, I have 4, so I will store it over here. And then I get 2, so I copy it here. And now I see, okay, so the next block of this message, so now I can send the message, okay, I have gotten number 2. So he can delete that. And then after some timeout, the sender decides that after a timeout, if it hasn't gotten an acknowledgement for number 3, it resends it. So then it resends number 3. Now number 3 arrives, he copies it here, acknowledges number 3, acknowledges number 4, and then he can delete that, and now number 5 arrives. Maybe it has arrived earlier, but whatever. So that's really the point of TCP, that you have these, you have this sequence number which tells you in which order the packets are supposed to be handled, and if things go wrong, it reorders the stuff. And if something gets lost, it's retransmitted. Okay. So, but for security reasons, because you don't want a malicious attacker to send TCP packets pretending to be you. So it's not a great way of protection against that, but before we have any transmission, the sender and recipient agree on an offset with these sequence numbers. So we don't start at 1, 2, 3, 4, 5. We start at 42, 43, 44, and so on. And just to prevent a malicious attacker from sending TCP packets and claiming to be the sender. Okay. So that's one of the reasons why we have this relatively well-known TCP-Handshake. So when in UDP, you would just send data to the recipient. And if the recipient doesn't even have a server running, it will just drop these packets, and you won't even be notified about that. So another difference between TCP and UDP is that when you connect to a different machine, you don't just instantiate a socket on your machine and that's it. You also send the data to the server and say, hey, I want to connect to you. Okay? So, and if there is no server running or the server is not, doesn't agree, so maybe you're on a blacklist or something, then the server will tell you, no, you are not connecting to me, and then you will know that you cannot send data. Okay, and that's this relatively well-known TCP handshake. So here's your server, here's your client. So the client first sends a message syn for synchronize. With this message it sends this offset. Then the server sends a message synchronize and acknowledge, and transmits its own offset. You know, they can have different offsets. These offsets should actually, for security reasons, they should be random, but we'll just have a hard-coded offset. And after that, the client sends another acknowledge message, and then the connection is established, and both sides can communicate with each other. Okay, so this is how the TCP handshake looks. And when you have an established connection, the graceful disconnect, there's also an ungraceful disconnect, but the graceful disconnect looks like this. The one who disconnects sends a fin. Then the other part, at this point there's no actual difference between client and server anymore. So the one who wants to disconnect sends a fin. Then the other one sends an acknowledge for that fin. After that, it also sends a fin. and then the one who wanted to disconnect sends another acknowledge, and then the connection is terminated. Okay, so in practice, it's common not to send two different messages for this acknowledge and this fin here. So in practice, you just send both with one message, so fin and ack. And yeah, why is that such a complicated disconnect? So when he sends a fin, then he knows, except for this final acknowledge, he won't send any more data. Okay, so this fin means I'm not going to send any more data starting now. Okay, so when that fin arrives, and except for this final acknowledge message, he can now be sure that he is not sending anything after the fin. So he can start a timeout of 2 minutes, and after these 2 minutes, every packet that has been sent by the sender either has arrived or is older than 2 minutes, because it must have been sent before this fin. Right? So then it's older than 2 minutes, and if it's older than 2 minutes, it should have been dropped by the network, and it will have been dropped by the network. So after this timeout, the other side knows, okay, there won't be any more messages coming from him. I mean, before this timeout, there could be messages that are just late. But after this timeout, there won't be any more messages, and then he can reuse the port number and the socket. Okay, so without risking that any older messages from him will go to a different application that is actually now communicating with a different guy. Okay, and it's the same on the other hand. So when he sends his fin ack, then he can start his timeout and say, okay, if I have this fin now, I can start this timeout, and after 2 minutes I know there won't be anything coming from him anymore. So I can reuse these resources. Okay. So yeah, if you take this basic behavior and you make a diagram of what can happen when can you get which of these messages. There is this nice diagram, also relatively well known here, which shows you different states that such a socket can be in. It starts out closed, then it can send a SYN, receive a SYN ACK, and send another ACK. Then it's established. Or if you are the server, you go into listening mode, you get a SYN, send a SYN ACK, go here, and when you receive the ACK, the connection is established. You know, this is just what happens here on both sides. And from an established connection, when the other guy sends a fin, you send an ACK. You get a fin, send an ACK. You should send also a fin and receive an ACK. Yeah, it's a bit strange here, but whatever. And here on the other hand, if you actively close the connection, you send a fin. Oops. You actively send a fin, receive an ACK, then you receive another fin and send another ACK. Okay, and this state here only occurs when when you send a fin and the other guy also wants to close the connection and has already sent also a fin, so you have sent a fin, you receive a fin, then you go into that state. So, this is how that works. So let's look at this TCP header. So what do we have there? Okay, you have 2 bytes for the port of the sender of the message, 2 bytes for the port on the destination side. Then you have 4 bytes for this sequence number. You know, this ID in this where am I in this stream? Then an acknowledgement number. So when you send some data and the recipient has gotten the data, it will send you an acknowledgement number to tell you, okay, now you can delete this much of your buffered message. That's in this acknowledgement number, and the sequence number is the thing that tells the recipient, hey, this is packet number 44. Okay? So, sequence number, acknowledgement number. Then you have 4 bits, which give you an offset. So the size of the header, but this is just a fourth of the actual size. So the size is counted in 32-bit integers. Then you have 3 reserved bits. Then you have 9 bits for flags. These basically contain these syn, ac, fin, and some other flags. Okay. Then after that you have 2 bytes for a so-called window size. This is, for example, if the recipient is just a little tiny device, using this number he could tell the sender, please don't send too much at once, okay? Give me small chunks. I don't have so much buffer to store, I don't know, 10 megabytes before processing it. Then you have a 2-byte checksum. Then you have a 2-byte urgent pointer. We will ignore this. One of the flags is the urgent flag, and if that's set, it basically means, hey, over here in this message, so here's a TCP message, and one of the flags says, hey, I have some urgent data, and this urgent pointer says, over here is the urgent part, so you can process this whenever you want, but this you should process immediately. Okay? And then after that you can have some options, just like with the IPv4, but I don't think we'll be using them in any way. The computation of the checksum is really complicated. I'm not sure I'm really going into that. But yeah, I mean, when you look at this, it mostly makes sense, I think. from what I've told you, source port, destination port, sequence number, acknowledgement number. This window size we will basically not really use. The urgent pointer we will basically not really use. The checksum is a checksum. The header size is an offset to the payload. And the last thing we should talk about before we start implementing this are these flags. So what are these flags? Well, first there are 3 flags. NS, I don't actually know what that does, and I think the Wikipedia page only says that it's somehow experimental. Then CWR and ECE. They have to do with congestion control. So if you send data and I don't know, your proxy server is under heavy load, it might tell you, sorry, I can't do it right now, send this later. Okay, that's for this, but we will ignore that. Then there's this urgent flag that I've already talked about, which tells you that this urgent pointer should be used, but we'll also ignore that. Okay, and then are the more interesting flags, the acknowledge flag, which tells you, hey, this is an acknowledgement message. So you can remove this many bytes from the buffer. Only if the egg flag is set, only then this number is relevant. Then there's the PSH flag, which basically says flush your buffer. So if you have buffered your data, then PSH says, so now you can something like, okay, so the complete message is, so the whole message is now complete, so you can now process it. So it's something like a flush your buffer message. Then there is an RST. That's a reset flag. And this was the graceful disconnect. The RST flag, the reset flag, is for an ungraceful disconnect. It basically says, don't send anything anymore to me. This is, for example, what you get when you try to connect a server or try to connect to a computer on a port on which there is no socket listening. And then there's synchronize, and the finalize, syn and fin here for the handshake and the graceful disconnect. Okay. So let's code this, but I'm warning you, this is really going to be a lot of code. So look at this. So these are 13 pages of code. Oh boy. So I guess this will take really some time. I guess it will take about 2 or 3 hours. But yeah, let's do this. Actually, I'm going to copy a lot from the UDP protocol. So So a handler has a handler can receive raw data from a TCP socket. A socket has a backend and a handler. The listening will be done in a different way. Yeah, we'll have to change this a little, but not now. Okay. TCP has the IPv4 ID 6, not 17. But we'll reuse all the stuff with the sockets. So here we set all the sockets to 0. We'll have a free port. This is what we do when we get an IP message. So this is where we will spend the most time, because for a lot of combinations of these flags, we'll have to implement different ways of handling this, depending on the state in this state transition diagram that we have here. So, and the connect will look a bit differently. The listening, the disconnect, the send. Okay, binding will stay the same. Sending, disconnecting, listening. Listening will be relatively similar, but yeah. Okay, so connect, receive, send, and listen. These are the things that we have to go into. And the first thing I'm going to do here now is I'm going to make an enumeration for the states that you have here. Okay. So every socket will be in one of these states, a closed state, a listen state, and so on. Okay. So the header looks differently. We have a source port, a destination port. A sequence number. An acknowledgement number. Okay. Okay, a socket has a remote port, remote IP, local port, local IP. It has a backend and a handler, and now it doesn't have this listening Boolean value. It instead has such a state here. So, the first thing I want to do is just change this listening method. So local port, local IP. Why am I doing it like this? Yeah, whatever. So when I'm listening on a TCP socket, I've removed this this listening bool, which I just had to set to true. Instead, I will just set its state to listening. So that's all you should have to do for listening. Okay, let's look at the sending. I think that that's not that hard. On the other hand, I think connecting and disconnecting is probably, okay, we will need the send for both of them anyways. So we instantiate a socket, set its remote port to the port that we want to connect to, local port to our own port, remote IP, local IP, and then switch the endianness. So we have to set the state. I mean, in the diagram, when we connect ourselves, we send the SYN and go to the SYN send state. But I will actually send the SYN only after the socket is connected to the TCP backend, because otherwise, maybe we would already receive an answer that we wouldn't get if we sent the SYN before setting the handler correctly. Okay, the backend is sent by this. We set the remote address, remote port, local address, local port. We need to store our own sequence number. In the socket. So the socket needs to know which number to send next as the sequence number. I will just set this to this funny hex word. So we put the socket in our list. And then we should send on this socket no data, but asynchronize. What is asynchronize? Okay, where do I define that? Okay, so this already looks nice, I think. So here we send 0 bytes of actual payload data, but yeah, we need to change the send so that it also accepts these values for the flags. Okay, how do we disconnect? Yeah, when we disconnect, we change the state. Actually, this removing the socket from this list is actually not done here anymore. This will be done in the handling of the appropriate message. So when we have received the last acknowledge, then we remove the socket from this list. So we actively close, that means we send the fin and go to fin wait 1. Again, we send no actual data. We only send a fin. And I think it's okay to also send an acknowledge. Yeah, I think it's okay to also send set this acknowledge bit. So that's the disconnect. Now, how do we actually send data? So I've just checked the running time of this video is already quite long. So I think I will just do the sending in the next video, which actually also makes sense because the sending also requires a certain checksum. So I think it kind of makes sense to stop here and continue in another video where we will also discuss this checksum. So tune in next time. Next time we will go into the sending of data through TCP connections. It's a bit harder than it sounds, especially because of this awful checksum there. But okay. So don't forget to subscribe so that you don't miss the next video on sending data. Hit like if you like this video, and see you next time. Bye.